looking at is I'll just be working through a past paper, the 2017 paper. And while we go through it, I'll be looking at different things and hopefully give you some tips and tricks of how to answer these questions. So what I'm showing on the screen is the link, first of all, to finding past NZQA papers and the assessment schedules and sort of other stuff too. So if I, for instance, swap this and I go to the link over here, I can make this a bit bigger. So this is that same link that's on that sheet. The achievement standard, you can see it's changed over the years, and you've got past exam papers. And so you can access them from here to 2019 and so on. There are some exemplars if you want to have a look at that. And it goes all the way to 2011. So there are lots of papers. If you do all of these papers in preparation, you deserve an excellence. Okay. And if you scroll further down, you can see the assessment schedules. So you can check your answers, or you can ask your teacher whether they can mark your work for you, because sometimes you might be a bit unsure whether your wording would have been acceptable for an examiner. So I always say to my students, just upload your practice exam paper from NZQA, not the derived grade ones, just into, say, for instance, if it's WAVES, the 104 3A Dropbox, and then I can do it for you. So you can see all these things here, and they're really useful. You will be also given a resource booklet, which I've shown over here. If you want to access this one, you need to just Google the 90937, because that's where they show the resource booklet. They don't show it with the 38 or the 39. But as you can see, it does cover all the formulae. So this is together with to do with electricity. This one is for the WAVES, which we're doing today. And then this is the one if you're doing the heat standard. So all those things will be given in the exam in a separate booklet, so make sure you're able to access it. Okay, so going back to this, please chip in and type in any questions if you want to ask me something about any of this. So if you look at the standard, basically they say, you know, we could ask you to write things, calculate things, graph things, or draw diagrams. And the WAVES, you do draw a lot of diagrams. Please make sure you bring a ruler into the exam room. So for the derived grade, you'll be doing it perhaps at home or wherever you've arranged for it to be done. Or if you're going into the school for the November exam, make sure you bring a ruler. Okay. So you will be drawing lots of diagrams. You will be looking at reflection and refraction of light, dispersion of white light through a triangular prism. So you need to know about, you know, the Roy G. Biv, the different colors, total internal reflection, and how the speed of light. Okay, then you also need to know the difference between longitudinal and transverse waves. You need to be able to also calculate things like period, wavelength, and frequency. And you notice that they give you 3 formulae, which are the ones that are given in the resource booklet. So you don't have to learn those off by heart. But just as my first tip, make sure you know what these mean, and also what the units are. So hopefully you know V, that actually stands for velocity. So if you're wondering why it's V, it's velocity. But at level 1, we just talk about speed. And that is measured in meters per second. Now that is important because sometimes they ask you to give an answer in centimeters. So if you're calculating in meters per second, you will need to make that change step from meters to centimeters later. So so that was V. D is distance. That's hopefully a nice. The formulae are, so you will be getting those both in the derived grade and in the November exam. As I say, it is a separate booklet. So if they give you an exam paper without the resource booklet, put up your hand and say, hey, where's the resource booklet? Because you do need that. You are not told, though, what V, D, and T are, and so on. You are expected to know that. So distance, and that is measured in meters. And again, as I say, if they ask you to give something in centimeters, you need to do that conversion between meters to centimeters. And then T, a small t, because it's important that you are aware the difference between a small t and a big T. Okay, they're different things, so don't just capitalize everything or make everything small. The symbol is important. So T is time, and time, hopefully, you know, is measured in seconds. And again, be careful if they give you something in minutes or hours. It's unlikely for the waves one, but, you know, because you've got to convert things to seconds. Because to make all these match up, meters per second, meters and seconds, I can't have meters per second, centimeters and hours over here, because they're not going to correlate with each other. So when you do the calculations, make sure that everything is in the right unit. Similarly for this one, we already know V is velocity. Hopefully you'll know F is frequency. And frequency, learn it as two different units. The unit of frequency is hertz, or Hz. That's my Z. But that is the same. 1 hertz is the same as per second. Okay, 1 over S. So those are the same thing. And sometimes it's easier to remember it as per second rather than hertz. 1 is obviously 1, it's a number, it doesn't have units. And then the capital T is the period. And that is also time. And that is measured, though, for 1 wavelength. So period is a time taken for 1 wavelength to go past. So if you've got 5 wavelengths, that time taken for the 5 wavelengths is not the period. You have to divide it by 5 to get the period. And so it's a time taken, so the unit is seconds. And you should be able to work out that these, if I've got frequency is 1 over seconds and period is measured in seconds, you can see why the hertz is the same as per second. Any questions on knowing the quantities, the symbols, and their units? Because if you know those, you will find the calculations quite easy. You all fine with that? Great. So let's get cracking. So here's the first one. As I say, this is the 2017 paper. I've just taken sort of screenshots so I can scribble using this one rather than trying with a PDF. So they often do give photos and so on, and that's to help visualize it more. So basically what we're saying, Mike's in the pool, there's something on the bottom of the pool, but he's seeing it up top there. So name the physics phenomenon. Now you hopefully can see that these are the same size and they're directly in line with each other. Okay, that line there is probably where the surface of the water is. I don't know. Well, no, actually that's the surface of the water up there. So what do you think is happening here? So hopefully you can think same size, there's reflection going on because it's in the same area. It's not as though this is the cleaner is sitting on the side. So hopefully you can say straight away it's reflection. And quite frankly, I haven't finished, by the way. Quite frankly, look at the wording and that can tell you, told you it's reflection. But it's not just any old reflection. it's a particular type of reflection, and hopefully you know it's internal, total internal reflection, sorry. So I'm just going to put that chat up so I can just see. Yep, great. Yep. Sorry, John, I'd missed your chat because I hadn't up yet. Okay, right. So that's just an achieved level mark, but it's hopefully a dead easy one. So go for it. Now let's carry on. If I go down, we need to draw a ray diagram to show it. So if you think of reflection, whether it's a reflection in the mirror, you expect it to be the same size, but and the same distance apart. So when you draw this, sort of try and be as accurate as possible, because that really does make a difference between achieved merit and merit sort of thing. So try and judge that area, and a ruler would help. So you want it to be pretty much that same distance above the air, and you want it to be the same size. Now, this interface is really acting like a mirror. Now, normally when you look at a mirror and you've got your left hand, and so your right hand and your left hand in your image, this becomes your left and that's your right, that sort of style. You've got that lateral inversion. So now here you can imagine this as being the mirror. Yep. And okay, I just see their screen. Yep. So what's happening if this is, say, the bottom down here and that's the top, then just sort of think sideways. So this is going to be the top and that's going to be the bottom. So can you see that the image is going to be upside down? It's going to be inverted. This will come in a later question, but whenever you're drawing this, it's a good idea just to try and imagine it in your mind, what's happening. So now you've got to pretty much draw it. And I would say, once you've decided where it's going to be, you've worked out your measurement, it's going to be there, take your sort of the top part. Now, actually, it tells you how many arrows to include or how many lines. It just says draw a ray diagrams. So you can just draw one single line. So pretty much what you want to do is draw a straight line going from Mike to there. Okay. And where the interface is, you're going to draw the normal. I always like drawing the normal. You don't have to, but remember, if you draw the normal, then it's very easy to take the angle of incidence to make it equal to the angle of reflection if you've got that normal there. And now hopefully not, I have not got a ruler, okay? So I'm going to just, it's supposed to go to that corner, sorry. That looks terrible. Let me try one more time, otherwise I'm not going to. So that's the way it goes, but I won't get anything yet because I didn't draw arrows. So draw arrows and, it goes the other way, sorry. Remember, it's always got to be the direction of the light traveling. So it's going from the pool cleaner to the person's eye. Okay. So this is the image. Now there's one more thing that I have not done. So this is not quite perfect. What do we know about solid lines and dotted lines when we draw ray diagrams? When do we use solid and when do we use dotted? Does anybody know? Okay, we use solid when it's an actual ray of light. We use dotted when it's not a ray of light. In other words, when the image is virtual. And mirror images are always virtual. So you need to, now I can't unfortunately rub this up. So this needs to be dotted. Now, I've drawn a line there. Perhaps you could, with a pencil, draw it lightly, and then go over it again to make a thick line there and a thick line there, and then make an arrow go to there and there. Does anybody have any questions about how to draw this? Did you see how I started? I more or less knew where it was, because if I didn't put that there, I could have drawn my, yep, so it's the dashed lines. I could have drawn my thing anywhere like that. And then my pool cleaner is rather too close to the surface. So try and work out where it should be, and then draw in your lines. Okay, so John, you said, where do they go? The dashed lines are always for the virtual. So actually, let me just tidy this up now. If I rub this out, the whole thing will go. So I'll just put my solid line there. So this solid line, this is an actual ray of light that's coming off, it's the sun reaches it, it bounces off the pool cleaner, so it goes back up to the surface, reflects, and goes into Mike's eye. So that is a real ray of light. This over here that's dotted is not, there's no light here, absolutely nothing. I could wave my hand in that space and I wouldn't be blocking the light at all, because there is absolutely no light from in this area. It's just how our eye fools us, because our brain says light travels in straight lines. And so my brain says, there must be a light ray there, but there actually isn't. So what's the opposite of the dashed line? A solid line. So can you see I've got a solid line, for this bit, because that's a real light ray, and I've got a dashed line for a phantom light ray, something that's not there. Okay, so the purpose of having it solid and dashed is just to show what is a real, what is real light and what is not real. Now, notice if you muck up your drawing, and it says here, they do not want you to scratch it all out and then try and redraw and scratch it all out. So it's very difficult to see. So if you've mucked up your ray diagram, you'll notice every ray diagram, they repeat it later on further down. So if you've messed this one up, that you've got to cross things out, do it again on the designated page, because we can't mark something that has just got lines everywhere and with squiggles over some of them, because that was wrong, and so on. Okay, now state two properties. So this is what I said, remember, of what the image is it going to be inverted and so on? And hopefully, because it's a reflection, hopefully you're going to say straight away that the image is virtual. Any reflection will be a virtual image. And the other one is you can say it's upside down, or you could say laterally inverted, because it is a reflection. It's just the mirror is sideways instead of upright. But it is that same idea. And the other thing you can say, because remember that it is a reflection, is the image bigger, smaller, or the same size? If you look at yourself in the mirror, are you bigger or smaller or the same size? Anyone? Nope. Okay, same size. So whenever they ask you for the properties, then it's always, is it virtual or real? Is it bigger, smaller, or same size? Or is it upside down or upright? Inverted or upright? So those are the three properties of images. And so you can put in all three, just in case you went wrong on one of them, and hopefully they'll still give you the achieved mark. But whenever they say describe the image or give the property of the image, it's always those things. Is it virtual or real? Is it bigger, smaller, or same size? Is it upright or inverted? Okay, chip in if you've got any questions. Right, now Mike's still in the pool, and he looks up and there's a tree close by, but he sees, oh, it's not quite where it's supposed to be in the garden. He sort of sees it a lot closer, actually. I mean, you don't, it doesn't actually say here, but when you draw it. So again, if you think about it, light from the sun is hitting this tree, and this tree is reflecting the light in all directions. So just take a point. Okay, I'm going to take the top of the tree because that is going to be the top of the tree of my image. I mean, you could take, say, that point, and then you know where the trunk ends. But so you just draw two light rays that are going to sort of be in the direction of Mike. So I'm going to draw one sort of like that. Again, please use a ruler, and I'm going to make this one go there. Okay. I mean, obviously the light is going in all directions, but we just want to just have in the direction of Mike. Then again, draw the normal. That really, really helps. Now, what's happening here is the light is going from a less optically dense to more optically dense. So my light ray is going to go what? Towards the normal. So on this side, is it now going to go closer to the normal so that that angle is bigger than this one? Or is it going to go away from the normal? It'll just go closer. Good. And that's why by drawing the normal, it really makes things easier. So it's going to go closer to the normal. Okay, doesn't. It's jolly difficult to draw freehand. Please use a ruler in the exam. As long as you make sure that this angle of refraction is smaller than the angle of incidence. And here again, this should be, again, the same angle of incidence, and it must be closer. Okay, it's not going to quite hit Mike. This is a terrible diagram, but anyway. Okay, so now we're going to put in the, and I'll just change my color, because now we need to remember our eye sees it's in straight lines. So we're going to extend this line as a straight line and extend that. Okay, so that it should come closer. Now, because this is so badly drawn, I'm just going to show you what the actual assessment schedule shows, because that's a much better diagram. Let me have a quick look at it here. And sorry, that's the exam paper. This one. And I'll just make it a bit bigger. And can you see how much nicer it is? So the point you need to have is that it's closer. Okay, but so they made the light rays much closer together, which I think made it easier. Mine were too far apart, which made it sort of harder, particularly when you don't have a ruler. Even if you made them further apart, it should still work. Although you want to try and get it within Mike's eye, because Mike is over there. You want to see what he's seeing and not what a person down here is seeing, which happened when you're showing my diagram. So that image up here is what a person down there is seeing and not what Mike is seeing. So it may be better to actually start from Mike, coming to think of it. I'm just going to rub this all out. Sorry for leading you astray. Yep, I think draw Mike's view first, and then you aim it to reach the top of the tree. So I'll start with a blue, and so make it go there and there, and now draw the normal. Try not to have it totally parallel, okay, because you do want it to focus on one point. Mine looks nearly parallel, but then you've got to make it turn away from the normal now, because I'm drawing out to a less optically dense, and so I'm just going to go like that, make it go. And now we're going to just extend the line Let's choose a different color. Let's make it bright green. And now we make it dotted line. And so where that point is, that's the same as that tree point. So this is where the tree is, as long as your tree comes closer. Yep, so make sure it goes, draw from Mike's angle. So start from Mike and do that there. Then, of course, what was the other thing? When you draw ray diagrams, they do want you to put in the arrows. So remember, the light is coming from the tree going to Mike. So draw the rays going to Mike. So if I quickly flip to where we were in the assessment schedule, he's put it that way. The light ray is actually coming from the tree going to Mike. I could check up on that, but I would have drawn it the other way he sees that. Okay, you could perhaps also ask your physics teacher, and for the ones that I'm teaching, I'll just check up on that because I would have definitely have drawn it the other way. Oh, let's go to the next question. Sorry, I didn't mean to give you the answer first. Apologies for my really terrible squiggles. Let's now look at this. Hopefully you know what that sort of wave is. Whenever you get sort of dotted things where there's lots of dots close together and then dots far apart, is this a transverse, pardon me, a transverse wave or a longitudinal wave? Not sure? Okay, so just, no, it won't be transverse. So transverse has an amplitude you can see. So a transverse will always be this sort of thing, because then it's very easy to see the amplitude. Okay, because the particles are bobbing up and down. If this wasn't a water wave, then that's sort of bobbing up and down in one position. So the more they bob up and down, the bigger the amplitude. Okay, so think of a water wave that's sort of going like that. That is a transverse wave. And we call it transverse because the direction of motion is like that, but the particles are going at right angles to it. So if that's the direction of motion, the particles are actually doing this, bobbing up and down. Whereas for a longitudinal, which this is, then the particles are bobbing backwards and forwards. So this sort of particle is bobbing there, and then it's bobbing that side, and then it's bobbing this side, and then it's bobbing that side. So it's in the same direction and opposite direction of motion, but not perpendicular to the motion. So transverse is perpendicular, longitudinal is the same. If you can think of a nice mnemonic to remember that, that'll be great. So this is a longitudinal wave. For the rest of you, is there any way you remember that this is a longitudinal wave? Or do you just sort of recognize it? Okay, right. Now here you'll notice long straight. Yes, that could be one way of thinking of it. Doesn't go up and down, it just goes like a one line. So that could be one way of thinking of it. Okay, you'll notice there's no picture over here, and that's because in the exam paper you would get a picture, but it's normally got some sort of copyright. So if you download from the internet, you don't see it. But normally, as I say, the picture's there just to make the question look interesting, and it's not particularly important. Okay, so here we've got a swimming pool with a speaker somewhere. So you can just imagine a swimming pool and there's a speaker somewhere. And we know that the pool is 25 meters. Now remember, if you know your symbols and your units, you know straight away that that is D for distance. Okay, so you know already which formulae you can look at because you know D for distance. So this is 25 meters. Now we know the sound takes less than 0.1 second to travel to the far end and back. So it's little things like this that become important because, you know, it will affect whether you get it right or wrong. So if you wanted to go there and back, then basically the distance here is going to be 2 times 25, which is 50 meters. Okay. Right. Now, if Mike and the speaker are underwater at one end of the swimming pool, determine whether you should be able to distinguish the echo of the sound off the far end of the pool and the speed of sound is. Now, if you see the word determine, that's just a fancy word for calculate. Okay, I don't know really. We had determined when we were at school, so it's sort of been around for ages. But if you see the word determine, think that means calculate, which means get the resource booklet and look at what's given. So I'm going to go shoot upwards over here, and you're going to go, right, I've got those 3 formulae. Which one of these am I going to use? So remember we had a distance. One was D. And we also actually had, although I didn't highlight it, we also had a V. So I'll get down to that now. So if you know a V and you know a D, can you see I can always calculate T? Do you follow? If you've got a question with 2 unknowns, then, sorry, if you've got a formula with 1 unknown and 2 knowns, you can calculate it. If you know V, then you have also got V over there. So this could be a possibility if we can work out either F or lambda somewhere. Because remember, distance, lambda, oh, I didn't actually say what lambda was here. Haha. Lambda is equal to wavelength. And of course, wavelength is also a distance, so it's also measured in meters. So if you get given a unit of meters, think of distance first, but chug in the back of your mind that it could also be wavelength. Now, obviously, a swimming pool distance is distance and not one single wavelength. So let's go back to the question. Over here, right. So that is the velocity. So that's V or speed. Oh, okay, right. I just saw your thing. So remember, V is equal to D over T. If you forgot or something like that, a good way is to see whether your units cancel. So meters per second must equal to meters over seconds. The units of distance is meters. The unit of time is seconds. And meters per second is the same as meters per second. If you had seconds is equal to meters, I'm just looking at your formula, meters per second times meters, can you see that's not the same? Because meters times meters is actually meters squared all over seconds, which is not the same as that. So you can use units to work out whether your formula was correct. Okay, let me just, I hope I didn't confuse everybody there. I hope I was just like showing how you can use units to see if they cancel correctly. So here you just simply plug and chug. You know the distance is 50 meters. Okay, he will be able to distinguish the echo of the sound of the far end of the pool. We want to know the time, so we've got to solve this for t. Yep, so t is equal to, if I'm dividing it this side, it multiplies that side, and then if that one's multiplying, it divides on this side. So it's d over v, which is 50 meters all over 1480 meters per second. And that's going to be a tiny amount. Okay. So it's going to be, 50 divided by 1480 is equal to, I get 0.03378. So I can change that to, because that's a whole lot of numbers, it keeps on carrying on. Because these are, that's just 2 figures, that one is 4 figures, but it's actually only 3 significant figures. That's strictly speaking just 2, because 25 times 2, so we know the 0 does count. So I would round this to 0.034 seconds. Now, we have to answer the question, would he be able to distinguish the echo of the sound? And we are told that if, I'll just change that color again, I'm just using lots of different colors. If it's less than 0.1 seconds, you won't be able to distinguish it. So is this less than 0.1 second? Correct. Okay, you'd be surprised how actually people see 3 and they go, no, it's more than 1, but it's 0.03. So because it's less, Mike will not. So make sure you answer the question. Mike will not be able to distinguish the sound or distinguish the echo. Excuse my terrible writing. And because it is less than 0.1 seconds. Okay, so make sure for like those excellence type things, give statements in your writing. Don't just make it a mess of numbers. If I go back to the assessment schedule, okay, so here they work it out. Okay, correct method, but did not double the distance. You just get an achieved. Or if you did the whole thing correctly, but you didn't put a statement in, do you see you only get achieved? So make sure you answer the question. The question said, didn't say calculate the time it would take. It said, would Mike be able to distinguish the sound? So you've got to answer that. So correct working and the answer, and I always say make sure you've got the unit as well, and that statement. Right, carrying on. Now we say while still underwater, we now have something like this. And you go, okay, what is this? I'll just change my color. What is that? That is hertz. So that is the unit for frequency. So we know that that is frequency. And we're asked to calculate the wavelength. Yep. So we've got the wavelength. So now you go back to your resource booklet and you go, okay, which formula has F and wavelength in it? So we go back up here again and we go, this has, because I need to calculate that. I'm given that and I was told the velocity earlier, so I know that. So we know V is equal to F times lambda. And so we're going to shoot back down here again. So we know V is equal to F times lambda. I want to get lambda by itself. So if F is multiplying here, it's got to divide on the other side. So we've got lambda by itself now is equal to V over lambda. So we just plug and chug. We know our velocity was 1480 because we were told that previously. meters per second divided by 1500 hertz, but I'm just going to make it per second so you can see that per seconds cancel out. And you know that should be really, really, really close to 1, okay? It actually comes to 0.98. I know that because I calculated it earlier. Oh, sorry. Yep, it should be around about that. So let me just do that again. Smaller number, 1480 divided by 1500 is equal to, yep, no, it's actually 0.99 because it's 986. But that is meters. Now, will I get merit or excellence for this question, depending on what level it goes to? Have I answered the question completely? Hopefully it says state your answer in centimeters. So whenever you've answered something, go back to the question and go, right, I've used that, I've calculated the wavelength. Oh, I didn't put it in centimeters. I need to do it again. And they actually even help you. Although I have found a lot of students just simply put whatever number they had there, they put it down here and they don't actually see the units. So I also strongly recommend you get your calculator and you multiply that by 100 because that's how many centimeters there are on a meter. So you get the 99, we can make it 98.7, or you could just make it 99 centimeters. I've just found a lot of people can't do those conversions easily in their head, and they sort of, it's out by a point or so. So just use your calculator. And if you look at that, they actually, yep, they've got a 98.7. And if you only get an achieved, if you leave it in meters, but if you do convert, then it gets to a merit level answer. All this other stuff is for another part of the question. So do you notice how it's important to answer every question? Because if you did this without doing anything for the next question, you can't ever get more than achieved, because you need to have all this other stuff as well to get the merit. Okay, or you've got to get 2 out of 4 of these points. So you've got to have the correct answer in centimeters and say something else in this part. Okay, we've got 15 minutes left. We better get going. Sorry, I meant to click on this. So when the speaker is floating on the surface of the water, it emits sound waves into the air and into the water. So this, whenever it's got this word explain, you know this is an excellence level question. So give as much detail as you can. Whenever you make a statement, so ask yourself, how? How do I know that? Why does that happen? Because it can be just simply obvious detail that you think is so obvious that you don't bother putting it in, but that's the difference between your achieved and your merit and your excellence. So do a sort of a logical sequence. So basically what we're saying that sound waves, water, because we're talking about the medium, water, molecules. If you're not sure of the chemistry, whether it's molecules or atoms or whatever, just talk about particles. So we'll just go about particles. Water particles are much closer together than the particles in air. Most people make that statement and then they sort of leave it there. You need to add more detail. So what does this mean? Okay, it means that because they're closer together, when water molecules or water particles vibrate, because that's what the sound wave is, it's a vibration, they are more likely to collide with other particles. Now you could say because they are closer, but we have really made that statement over there. So what does that do? If they're more likely to collide, they are more likely, therefore, will pass on the energy. Because that's really what a sound wave or light wave is. It's passing on the energy, pass on the energy more easily or quickly or something along those lines. Okay. Water is more dense than air because it's a liquid. So liquids are always more dense than gases. Solids are usually more dense than liquids, but there are exceptions, and water is actually one of those exceptions. Water at 4 degrees centigrade is more dense than ice, but metals are more dense than water. So you'll have sound traveling through, say, metal pipe much more quickly than it would through water. So you've basically got to say, describe what it is. So if they're closer together, what will be the effect? It's because when the sound wave goes through, they vibrate, and therefore they will more likely collide, and therefore they will more likely pass on the energy. But now we haven't answered completely because we haven't answered this bit. How is it different? So we need to say, you could actually, by the way, Harry, you could say water is more dense than air as part of your description. So you can include that. And therefore you can say, therefore they are closer together. So you could add that in your explanation. But we've got to say the how. So therefore sound waves travel faster through water. So it's all those points that you've got to have. Make sure you answer the question. So how goes faster. Oh, we lost Harry. And we've also got to say all the bits and pieces. So if we again look at, let me just go, where was I? Hopefully Harry's back. Yep, okay. You must have lost a connection. So since water is denser than air, so that's the how part. They'll travel faster. And now this is all those little bits in between, the how and the why, so that there's going to be more collisions. Okay, they haven't done it quite, but they have mentioned the energy transfer. Okay, and they've talked about the interaction between particles. So I spoke about collisions between the particles because they're closer together. They've said denser, but I've said closer together, but so the same ideas are there. And you can also talk about describing in terms of a formula. That's always useful. Remember, frequency is not affected when it changes medium because the frequency is determined by the source. So my larynx is giving a frequency. Okay, it doesn't change because from getting from me to you, doesn't matter what pathway they choose, the sound waves have the same frequency. They may go faster and slower, through the wire or whatever, but it's still the same frequency. So here they've used the lambda or this formula over here to explain. So that is another way of doing it. Right. 10 minutes left. Let's do the last question. Oh, okay, it's not quite. So Mike gets out the pool. He decides to experiment and asks his friend Paddy to stand behind a wall. So if it was a light wave, if it goes in straight lines, but waves can bend. And there's a particular word for that. And that is, hopefully, is as diffraction. So remember, you have to know in the exam, reflection, refraction, diffraction. So diffraction is the bending of the light waves. when it's going through a gap. Okay, and so basically you had to draw these. Now remember what I said about the frequency not changing? And here, because it's in the same medium, the wavelength doesn't change either. So when you are drawing this sort of diagram, measure how far apart that is, and then, you know, do little things like this to keep to that same wavelength, okay? And then use a ruler to draw that, and that it starts bending. So use a ruler and then just use freehand to do the last bit to show the bending. So can you see, though, I've tried to as much as I possibly can with a freehand to keep the wavelengths the same. So you're not going to do well if you have differing wavelengths. There will be differing wavelengths if you're making the wave go from deeper water to shallow water, or from shallow water to deeper water. But in this case, we're not told anything about that. So we assume it is the same depth of water, so the wavelengths are not allowed to change. Any questions about that? So I can flick through to this and notice that they say here, for merit, you've got to have the constant wavelength. So if you just draw it roughly, you're not going to get more than achieved. And if you set diffraction and you drew the diagram, you're still not going to get more than achieved if you've got funny things over here. Right. We're just about on the last question. Okay, so here I'm not going to write as much because we've only got about 7 minutes left. Here we've got something, and now we've got to describe how the speed of light changes when it enters a higher optical density. So hopefully from less optical to more optical, you will say that the speed of light slows down. Okay, now you asked about the speed of light and not how the light bends or something like that, but you could put that in if you wanted to, but that's the key thing, that it slows down. Now you want the next one. As it travels through the test tube, it passes through different mediums, and you should know that air is less optically dense than glass. Remember, always draw the normal. So always draw it at right angles. So as it's coming through here now, you've got to, you're going from less optically dense to more to less. So this needs to go towards the normal. Okay, I'm not doing it very well. Then you draw it, another normal, and then you draw it going away from the normal. Now, when you draw it going away from the normal, this is a very bad diagram because this light ray over here should be parallel to that light ray over there. Okay, so if those aren't parallel, you've not drawn a very good diagram like this one. This is not a good diagram, but you get the idea. So again, just flicking through onto this bit. Oh, sorry. If I scroll down, that's a much better thing. Can you see that that ray is parallel to that ray? So if I extended this one back, that sort of extended line should be definitely parallel to that one. Okay, so rays in the air are parallel. You do need to have that. Okay, let's now go to the next question. And again, if you stuff it up, just go to the new diagram further down. Now, this is an interesting one. We are basically told, right, I've got a container with a glass test tube inside. And I'm going to fill that glass test tube. Yes, you could do that. You could do that. So for those that didn't see the chat, Madeline said, could they first draw the main line, and so they can see whether it's parallel or not, and then draw the bending line in between. So yes, you can do that. Okay, so air has a lower optical density than glass and peanut oil. So here inside this, we've got air, so we can see the tube. But now we're going to fill this test tube with peanut oil. So you can see here there was much, now we're filling it more, and now it's completely gone. Okay, so that's what's happening. Spend a bit of time making sure you understand what that is showing. Then it says, it looks as though the test tube's disappeared. Why? Okay, now you first, you don't know the answer to that yet, but we'll get there. But you first need to do what happens. Complete, so we're going oil, glass, oil. Oh, it does, we do need something else before we can do this. We need to know the optical density of the peanut oil. Right, this is where it is. So can you see, I couldn't actually answer the question until I knew what glass and peanut oil is. And they're the same optical density. So if they're the same optical density, you actually just draw the straight. You just take your ruler, match it up with that, and just draw it straight. Okay. Let's make it go straight through. Yes, I know there's a difference between oil and glass and oil, but quite frankly, the glass is actually so thin it hardly does anything. So you just make it go straight through. That's the easiest way to do it. Because, oh no, please rewind. We were told specifically that glass and oil have the same optical density. And if they have the same optical density, there's not going to be any refraction. Sorry, just scrub out what I said slightly earlier. There's a difference between the air and the glass and the peanut oil. And so now here you just need to explain all that. Oh, you don't. Okay, so that was interesting. Lots of diagrams, but you don't actually have to explain. Here now this is tricky simply because it can be a pain to draw. So I'm just going to show you the assessment schedule because it'll be a lot quicker. So the first thing you can see when you're drawing this is, can you see that that is parallel to that? So Madeleine, using your same tip, you could sort of extend that line on and make sure that the line you draw lower down is going to be parallel with it. Okay, because we're going through air and it does its separation and coming together, and so it'll come out at the same angle. And then here, just simply, I always suggest you put in your normal and you make one turn slightly towards the normal and the one a lot more towards the normal. Hit the other side, draw on your normal, and then of course it bends away and then towards, and then here again, it's got to go away again from the normal. So this one's a bit clunky to do, but if you start off with that being parallel to that, then just as long as you make it spread out and then come together again. Any questions on that? Okay, so the final thing is basically you've got to explain. And we have reached 3 o'clock, but so that whole explanation is, as I say, spell out the obvious. The last, if I look over here, you'll see that the last question normally always has the word explain in it, and that's all the excellence. All the ones below, above in question 3 were either achieved or merit. Here, this one was question, okay, surprisingly that wasn't, so there's the excellence level. Yep, it's the refraction of the light colors, the Roy G. Biv. Okay, but here again, Oh, okay, so this one, the last one, normally the last one is always excellence level, but it isn't quite here. It goes up to merit level. Diagrams tend to be merit level unless they're very complicated, and explanations tend to be excellence level. So you can see the same thing here. Here you had to draw the diagram, but you had to explain as well. So do all the hows and the whys to try and explain. So, notice while red refracts the least, you could also talk about because it has the longest wavelength, add in the extra detail to show you've really understood it. So that's it. I've gone slightly longer. Any questions? I'll stop recording in the meantime. Sorry, this silence is while I'm trying to get my thing to work to stop recording.